Picture a factory assembly line. Each station adds one part, then passes the product straight to the next, and no station ever sits idle. That single image is the entire trick behind our topic today. When a network grows so deep that its layers cannot fit on one GPU, we can lay those layers out across several GPUs and let batches flow through them in order, exactly like items moving down the line. But there is a subtle trap hiding here, one that can leave most of your expensive hardware sitting idle, and the fix for it is genuinely elegant. Let's walk through how it all fits together. First, let's see the wall this technique is built to break through. Placing the entire model on a single GPU works fine for small networks. But modern architectures stack hundreds of layers with billions of parameters, and at some point the weights, activations, and gradients simply overflow the memory of any one device. The network is too deep to fit, and training stops before it can even begin. This approach takes a different route. It slices the model between its layers and hands each slice to a separate GPU. The first device holds the opening layers, the next holds the following group, and so on down the chain. So every GPU stores only its own share of the network, and the full model never has to live in one place. This between-layer split is exactly what sets it apart from tensor parallelism, which instead divides the math inside a single layer. So how does a batch actually move through this line? Watch the sequence unfold, step by step. Begin by cutting the network into consecutive groups of layers and assign each group to its own GPU. Every device becomes one station on the line, responsible for its own stretch of the model and nothing more. Now, take the incoming batch and break it into many tiny micro batches. Instead of pushing one big block of data through the whole chain at once, we feed a steady stream of small pieces, one right after another. Send each small piece through the stations in a staggered rhythm. While the second GPU works on the first piece, the first GPU is already starting the second, and the wave keeps rolling forward through every stage of the line. Once the pipeline fills up, every GPU is processing a different piece at the same moment. So the idle gaps, the so-called pipeline bubble, shrink to almost nothing, and the hardware finally works together as one. Strip it down, and three ideas carry the whole technique. It splits a model across GPUs by layer, like an assembly line. Each device owns a consecutive block of layers, and data flows from one stage to the next in order, so a network far too deep for a single card can still run. Feeding many small pieces keeps every stage busy at once. By streaming them through the pipeline in a staggered pattern, the wasteful idle bubble nearly vanishes, and all the GPUs compute in parallel rather than politely waiting their turn. Its communication is light, so it scales across machines. Only the activations at each stage boundary get passed along, point to point, which means it tolerates the slower links between separate servers far better than methods that synchronize on every single layer. Push tensor parallelism across those same slow connections, and its constant chatter would quickly swamp the gains. All right, let's lock in what matters. This method places different groups of layers on separate GPUs, then streams data through them in order, exactly like a product moving down an assembly line. The catch is the pipeline bubble, the idle time when stages wait on each other, and splitting the batch into micro batches solves it by keeping every GPU working on a different piece. Because only the activations at stage boundaries travel between devices, its communication stays light, letting model size scale across many machines even when the links between them are slow. It usually teams up with tensor and data parallelism to train the very largest models on Earth. If breaking down big machine learning ideas this way clicks for you, we have plenty more waiting at Standarity.com. Come build with us.